Suppose we've got a list of independent random variables. Guess not necessarily identically distributed, though that would be the main application, right? Mostly we would think of these as being identically distributed, as being a random sample, having the same distribution. But what I'm about to say would apply even if they have different distributions. This is a theorem. What's the moment generating function for their sum is the question. Why would this be important? Oh, it's probably related to means, wouldn't it be? Because means are sums divided by n. It's the product of their moment generating functions. You could call it that, maybe the key moment generating function theorem or something like that. Well, there's the fingerprint theorem, which is also important, but that one already has a name. This is very powerful. In fact, you don't typically do this, but about 2 weeks ago, something like that, we used double integrals to figure out the distribution of x plus y when they're independent. I think for an exponential and a uniform, it involved tricky double integrals. Yeah, that was complicated. You remember that? We had to do tricky double integrals over triangles. Oh, this is easier. This is easier. In fact, let's go ahead and apply it to one of the examples that we did. One of the examples we did was for an exponential distribution. Say x and y are exponentially distributed. Remember, you can call the parameter either beta for the mean or lambda for the rate parameter. I don't remember offhand which is easier here, but let's write it in terms of beta. Beta is the mean. And these are independent. We're assuming independence, right? That's always an assumption so that we can actually do something. I just peeked at the table at the moment generating function for an exponential because I was afraid I was going to get it wrong. Right there. Exponential distribution with parameter beta. Beta is the mean. If it were a lambda that we were using, instead of beta times t, we'd write it as t over lambda. It's 1 minus beta times t to the negative 1 power. So the moment generating function for their sum, since we're assuming independence, is the product of their moment generating functions. But they both have the same distribution, so this is just really the same function times itself. If I use negative 1 power, I could write it like that. Yes, you could also write that as a fraction. And that can be rewritten by adding the exponents. Negative 1 plus negative 1 is negative 2, right? Careful. It's not 0. Negative 2. Okay, so well, how's that helpful? Fingerprint theorem. Oh, that doesn't have a negative 2. Hey, but that does if alpha is 2. What's that? Gamma. X plus y therefore has a gamma distribution, alpha equal to 2, and beta is the same beta as before. The fingerprint theorem now implies that x plus y has a gamma distribution, alpha equal to 2, and beta is the same beta that we assumed at the start. That was something we derived with integrals a couple weeks ago. Yeah, it wasn't fun. This is much more fun, much easier. What's the proof of this like? Well, it's fairly easy actually, though the book doesn't fully prove it really. It assumes if x and y are independent, then e to the x and e to the y are independent. Okay, I don't know if that's a difficult proof or not. I haven't thought about that. But the proof of it, which they do in the case when n is 2, is fairly short. So this is an application of this theorem. Your homework's going to have more applications. One big application of it That's actually an example in the book. Oh, is that, let's see. If X1 is, wait, I think all these Xi's have the same distribution. If these are all normally distributed with the same mean and the same variance, and if you add them, get a total, then you can figure out the distribution of the total by using this theorem and using the moment generating function for a normal. You will get a normal oh boy, you remember the mean? I think the mean makes sense to be n times mu. The variance is n times sigma squared. That's the distribution of the sum. What about the distribution of the mean? That's the cornerstone theorem. X bar, the mean, is normally distributed with the same mean as the population, and variance equal to sigma squared over n. That's what Dr. Wetzel wrote up on the board. How you get from here to here, it's just some properties of expected value, I think. And moment generating function and fingerprint theorem if you want to be extra precise about it. Okay, the homework is going to involve some kind of theoretical problems where you're doing this kind of thing. We're out of time, but let me also just encourage you to make sure you carefully read the central limit. Oh, I've been saying it like this, the central limit theorem. And also read about confidence intervals before class next Tuesday.